When you look up at night, the stars appear trapped inside a flat blue dome, hiding the reality of a three-dimensional universe spinning around us. Long before the invention of the telescope, early observers decoded these mechanics using nothing more than sticks, dirt, and sunlight. By driving a 1-meter stick into flat ground and marking the shadow's tip throughout the day, you see a consistent arc. This motion acts as a physical record of the Earth rotating beneath your feet. These basic measurements formed the blueprints for city-sized observatories. Locations like the Jantar Mantar use towering stone walls to track these shadows with enough accuracy to calculate the time and date. If you continue this experiment over a full year, you'll find that the sun's path is never static. The position of its shadow at noon today will be slightly different from its position 2 weeks later at the exact same time. This shift tracks the sun as it appears to move north and then south. These specific cycles are known as Uttarayanam and Dakshinayanam. These movements serve as markers that predict the arrival of summer and winter. If the Earth sat straight up and down, that noon shadow would remain the same every day of the year. The constant fluctuation of the shadow's length provides our first piece of spatial evidence that the Earth is tilted on its axis.
Each phase represents a specific coordinate in the Moon's monthly journey around us. With the Moon completing a full orbit every month, it should pass directly in front of the Sun. Yet total eclipses remain rare. The Moon and Sun follow slightly offset paths. Their orbital rings are tilted, so the Moon usually passes above or below the Sun. An eclipse only occurs when both reach the intersection of their paths simultaneously, and the shadow dot locks onto Earth. These events demonstrate the precise celestial positioning required for these bodies to cast a shadow across the void. While most stars seem to drift overnight, one point in the northern sky stays perfectly still, the pole star. To find it, observers used constellations like the Great Bear. Drawing a line from the 2 stars at the edge of its head leads directly to that stationary point. This globe reveals the physical reason for that stillness. The pole star sits directly in line with Earth's rotational axis, making it the only point in the sky that remains fixed as the planet spins. The spinning night sky is a reflection of the rotation occurring right under our feet. Against the fixed backdrop of the stars, a few bright objects move independently. These are the planets, which move across the sky by reflecting the sun's light. Mercury sits closest to the sun's glare, followed by the backward-spinning Venus and the dusty, cratered surface of Mars. Beyond the inner rocky worlds lie the gas giants like Jupiter and Saturn, alongside comets that travel in long elliptical orbits. Classifying this system requires strict criteria. In 2006, the International Astronomical Union voted to reclassify Pluto because it had not cleared its own orbital neighborhood. The solar system is a vast neighborhood defined by these predictable gravitational paths. The shifting noon shadow, the Moon's phases, and the fixed position of the pole star are the basic building blocks of our spatial understanding. These data points allow us to build a 3-dimensional model of the solar system, mapping the orbits and rotations of everything in our neighborhood.
Exploring the cosmos doesn't require a multi-billion-dollar spaceship. It starts with a clear sky and the curiosity to look up.